Welcome, everyone. It is Wednesday, April 1st. We are going to continue with a lesson from a previous class, so feel free to review that if you find it necessary. Our agenda today is to use the rotation formulas we developed to eliminate an XY term to be able to express a conic in standard form. And once again, you can review in the textbook the standard form of all conics we've been looking at, the parabola, the ellipse, and the hyperbola. There's an assignment available to you on Google Classroom 4-1 problem set. So here we go. And once again, I remind you, the next couple slides are just a review of the previous lesson. Feel free to skip through them if you feel very comfortable with it. I have myself a conic. I cannot complete the squares because of the XY term. So step number one for me is to be able to identify a particular angle of rotation to use to eliminate this XY term. If you remember, there is a formula we developed called the cotangent of twice theta is going to be equal to A minus C over B, 1 minus 2 over the square root of 3, negative 1 over the square root of 3. If you remember correctly, cotangent is defined in quadrants 1 to 2, which is from 0 to 180 degrees, 0 to pi for all you people who prefer radians. At this point in time, I do recognize that these values are telling me about a 30, 60, 90. It allows me to understand that the reference angle is 60 degrees, but it is a negative, so I must be in quadrant 2. So an angle of 120 degrees would have a reference angle of 60 degrees in quadrant 2. Therefore, 2 theta is 120 degrees, and divide both sides of this equation right here. 2 theta equals 120, gives me theta is equal to 60 degrees. Please do not assume that theta is 60 degrees because the reference angle was 60 degrees. That is just a coincidence of this particular problem. From there, now that I have my angle of rotation necessary to eliminate an XY term, I then went and I developed the rotation formulas. Once again, I remind you, you guys did a lot of good work to understand where these two equations come from. So I simply substitute 60 degrees in for theta in both cases. I recognize that the cosine and sine of 60 degrees is going to be 1/2 and square root of 3/2 respectively. So everything gets inputted where it belongs. I myself like to pull out common factors, avoid fractions as much as possible. Number one, it's easier simply to write. Number two, I've found through experience that you guys tend to make a lot less mistakes when there's a lot less complicated numbers to work with. So I like to express things in this particular form. Now we are going to move forward with today's lesson. It's going to be a relatively quick one because it's just all about algebra. You have identified the angle of rotation. It enabled you to then develop the actual rotation formulas. Now is the time to take those rotation formulas and to substitute them back into the original equation and make sure that you simplify this equation to the best of your ability. This is where mistakes are going to occur, but there is a checkpoint. If you substitute in your two formulas, x's for x's, y's for y's, let the math run its course. There's root 3's being multiplied in here. There's terms being squared. There's addition, subtraction. And you end up with still an x prime, y prime term. It is just communicating to you that you have made a mistake. Do not be quick to erase everything. Simply take the time to go back and revisit your calculations and see if you can find it there. So what does this look like? Well, the first step is exactly what you think it's going to be. What I decided to do is, since x is being squared, I just simply squared the 1/2 because these are factors, and then I squared this particular binomial. And hopefully I did not make a mistake. I then have a root 3, there it is. I have an x times a y. So I did 1/2 times 1/2, which is 1/4. And then I took this binomial and I multiplied it to that binomial. And hopefully, once again, I did not make a mistake. I then have a 2 out here. I do have y itself being squared, so I squared the 1/2, which gives me 1/4, and I squared this binomial, which gives me this right here. And then I took this 10, I simply moved it to the other side of the equation by adding it. So that equals 10. Now, ladies and gentlemen, once again, I only show enough work through experience to avoid mistakes that I've made somewhat relatively consistently. And the more you can do that, the more you can avoid this. All you mathematicians, applied mathematicians out there, remember, I'm paying you a lot of money to make sure my satellite is going to head off into space. And if you make one calculation error, it's billions of dollars of lost investment. That's why A, you're working a stressful job, but B, more importantly, that's why I pay you. I pay you for those skills and your ability to understand numbers, the relationships, and to avoid error. So what would I do? And I remind you once again, it's not necessarily what you would do. That's up for you to develop what approach works best for you. I do notice that these groups of factors, there's one group, there's another one, there's another one, do have some fractions in here. So what I think I'm going to do just to clean it up is I'm going to multiply the entire equation by 4 just to deal with that 1/4. You don't have to do that if you don't want to. At the same time, I'm going to recognize there's a √3 here. I think I'll distribute it through. There's a 2 right here. I think I'll distribute it through to there. So taking that all into account, but apparently I did take the time for you guys to just show you what happens when you multiply an entire equation by 4. This point in time, as you can see, there's nothing going on with this. There's no need to write the parentheses. My motto is if I don't need to, I'm not going to. Saves me time. I'll distribute the √3, distribute the 2, and that leads me to this jumbled mess right here. Now, notice that the equation is technically getting a little smaller, so that should make you feel relatively good. It is simplifying to some extent, but now it is the opportunity for me to have my checkpoint. Will the x prime, y prime terms actually eliminate? Well, let me identify them. Looks like I got -2√3 of them here. And I got -2√3 of them here. So there's -4√3. And I have 4√3 of them here. So there we go, people. Successful. -2√3 of them minus 2√3 of them is -4√3 of them plus 4√3 of them would give me 0. I may have made a mistake in all these other terms. The fact remains, at least I was able to get this correct. So there we go. Nicely done by us. Now it's just a question of simplifying the equation and combining all like terms. When I do that, that leads me to this right here. And you yourself can check all the calculations. Often I've had students who simply like to cross numbers out to make sure that they don't miss any numbers and or double count. So my x prime terms, there's 1, and there's now 4 of them, and there's 6 more of them, there's 10 of them. My y prime terms, there's 3 of them, there's -3 of them, so now I'm back to 0, and now I have 2 left over. And if I go through everything, everything's been marked off or underlined. I've done everything to the best of my ability. So I successfully substituted in the rotation formulas as far as I know. I've simplified the equation. And now the next step, of course, is always to get that equation to standard form. And so I am going to complete the square to express it. Now, of course, I've chosen an easy problem for myself. There's no need to complete a square because there is no x prime term and there's no y prime term. So all I need to do is set this equation equal to 1 by dividing both sides of the equation by 40. And that leads me to this. We are not going to take the time to graph that. That was the objectives and goals of a previous lesson. Right now, we are just working on the algebra of being able to rotate the axes. So ladies and gentlemen, once again, this is an ellipse. You should recognize where the foci are, where the vertices are, where the center is, where the endpoints of the minor axis is. You should then be able to rotate the axes, if you remember, a rotation of about 60 degrees. And there we go. And that is all we're going to work on today. Have a great day, and make sure if you have any questions, feel free to fire away to me via email.